You hear that rumbling sound approaching from miles away. The rhythmic clacking grows louder as tons of steel roll past your car at the crossing. But have you ever counted what's actually underneath that train? Wheel after wheel after wheel, sometimes stretching for what feels like forever. Meanwhile, your car sits on exactly 4 wheels, supporting maybe 4,000 pounds total. Yet that train carries the equivalent weight of thousands of cars on what seems like just a handful more wheels. The math shouldn't work. The rails should buckle. The wheels should sink straight through. But somehow, this massive machine glides effortlessly on 2 thin strips of metal. So what's really happening underneath all that rolling weight? The numbers are staggering when you actually break them down. A single fully loaded freight car weighs between 125 and 140 tons. That's roughly 60 to 70 times heavier than your average passenger car. Now multiply that by 200 cars in a typical freight train, and you're looking at more than 25,000 tons rolling on just 800 wheels. Compare that to your car's measly 2 tons on 4 wheels. The math becomes even more perplexing when you calculate the load per wheel. Each train wheel carries over 60,000 pounds of weight. Your car tire? About 1,000 pounds. That's a 60-fold difference. Common sense tells us that more weight should require exponentially more wheels. But trains completely defy this logic. And understanding why reveals fundamental physics principles that govern everything from how bridges support traffic to how aircraft landing gear is designed. To understand this apparent contradiction, we need to look back at railway history. The early 1800s saw numerous rail disasters where trains literally broke through tracks due to poor weight distribution. Engineers quickly realized that simply adding more wheels wasn't enough. They needed a completely different approach. The breakthrough came in the 1830s when railway engineer John B. Jervis introduced multi-axle bogies. This innovation transformed rail transportation, creating a clear evolution from horse-drawn rail cars to single-axle engines, then to multi-axle locomotives, and finally to the modern 6-axle freight engines we see today. The key innovation was the truck, or bogie system, that swiveling framework beneath train cars that holds multiple wheel sets. This seemingly simple mechanism revolutionized how weight could be distributed across rails. And despite centuries of technological advancement, this core principle has never changed. It all comes down to the basic physics of pressure distribution. So how do trains actually distribute these impossible weight loads? 4 fundamental principles explain everything: ground pressure, contact area, axle load limits, and dynamic distribution. It's similar to walking in snow with regular shoes versus snowshoes. The person weighs exactly the same, but snowshoes spread that weight across a much larger area, dramatically reducing pressure at any single point. There's a common misconception that trains simply have more wheels for more traction. While that's partially true, it's an incomplete explanation. The real answer lies in a basic physics formula: pressure equals force divided by area. More contact points mean lower pressure per point. This is the crucial difference between rail and road transport. Cars optimize for efficiency, while trains optimize for load capacity. Let's get technical for a moment. In North America, standard rail limits allow a maximum of 315,000 pounds. That's 157.5 tons per axle. This enormous weight spreads across 2 wheels and their contact patches with the rail. The relationship between axle load and track wear follows what engineers call a fourth power relationship. This means if you overload an axle by just 25%, you cause more than double the track damage. Overload it by 100%, and you're looking at 16 times more track wear. This explains why weight distribution is so critical in railway engineering. The bogie or truck system is brilliantly designed to handle this challenge. It consists of 2 levels of suspension: primary suspension between axles and the truck frame using steel springs, and secondary suspension between the truck and car body using airbags or additional springs. What makes this system truly remarkable is its load equalization capability. The weight automatically redistributes across all wheels, even as the train navigates curves or traverses uneven track sections. This dynamic response system constantly adjusts to track irregularities, ensuring that no single wheel bears excessive weight for extended periods. The physics of weight distribution becomes clearer when we examine a modern 6-axle locomotive. These massive engines weigh around 400,000 pounds, but distribute that weight across 12 wheels. Instead of a crushing 200,000 pounds per axle, each wheel only carries about 33,000 pounds. Still substantial, but manageable for properly engineered components. Then there's the matter of the contact patch, that critical point where wheel meets rail. Despite supporting tons of weight, each wheel creates a surprisingly small contact area with the rail, roughly 1 square inch. This is possible because of the material properties of steel. Steel-on-steel interfaces can handle extreme pressures that would instantly destroy rubber tires on asphalt. In practical operation, this engineering marvel requires careful management. Freight cars must follow precise loading sequences to maintain proper weight distribution. Sophisticated wayside detectors continuously measure wheel loads to identify potential problems before they cause accidents. Engineers calculate maximum safe speeds on curves based partly on weight distribution factors. And maintenance schedules for track inspection are determined by the accumulated tonnage and axle loads that have passed over a section. Modern railways also employ safety systems that prevent overloaded cars from entering service. Weight-in-motion scales identify cars exceeding axle load limits, flagging them for adjustment before they damage track infrastructure or create unsafe conditions. To me, that's the real genius of railway engineering. It's not just about adding more wheels, but implementing precisely calculated pressure distribution systems. This same fundamental physics applies well beyond railways. You'll find it in aircraft landing gear design, heavy machinery operations, and even building foundation engineering. The multi-wheel design of trains represents one of transportation's most elegant solutions to a seemingly impossible challenge: moving massive weights efficiently over relatively fragile infrastructure. The wheel arrangement isn't random. It's a carefully calculated distribution system that optimizes for capacity, safety, and infrastructure preservation. Understanding the mechanics of train wheels also reveals why tracks require such precise maintenance. Even small imperfections can disrupt this delicate balance of weight distribution, potentially leading to accelerated wear or even derailments in extreme cases. This explains the railway industry's obsession with track geometry and alignment. They're protecting their most valuable asset: the ability to move tremendous weight on minimal infrastructure. What's particularly fascinating is how this weight distribution system has evolved alongside increasing train weights. Early locomotives weighed just a few tons, while modern ones exceed 200 tons. Yet the basic principle remains unchanged: distribute weight across multiple axles to protect the track. The economic impact of this engineering solution is staggering. Without multi-axle bogies, rail freight would require either dramatically reinforced tracks at enormous cost or significantly reduced cargo capacity. By solving the weight distribution problem, engineers enabled the modern rail freight system that moves billions of tons of goods annually at a fraction of the cost of road transport. The efficiency gains are equally impressive. A train with properly distributed weight experiences significantly less rolling resistance than one with poorly balanced loads. This translates directly to fuel savings and increased operational range. Some estimates suggest that optimal weight distribution can improve fuel efficiency by 15 to 20% compared to poorly balanced alternatives. We also see this principle at work in specialized rail applications. Heavy haul operations in mining regions use cars with additional axles, sometimes 12 or more per car, to carry extraordinary loads over relatively light track structures. These specialized bogies distribute weight so effectively that they can carry ore loads exceeding 400 tons per car without damaging infrastructure. There's an elegant simplicity to this solution. Rather than building ever stronger infrastructure, engineers found ways to work within existing constraints by distributing forces more intelligently. It's a lesson in efficiency that continues to influence transportation design across industries. Next time you're waiting at a railroad crossing, counting the seemingly endless parade of wheels, remember you're witnessing one of engineering's great achievements. Not just more wheels, but precisely calculated pressure distribution that makes modern rail transport possible. And now I'm curious, have you ever wondered why train wheels are shaped the way they are? Those flanged edges and tapered surfaces aren't just for show. They're part of an equally brilliant solution to another fascinating engineering challenge: how trains actually steer without steering wheels.